Hello, welcome back to another Eviews video tutorial. My name is Juan and today I'm going to be covering the topic vector autoregression bar models in Eviews. So let's begin with an overview of bar models. They are bar models generalized univariate autoregressive models by allowing multivariate time series. So recall that a univariate regression is a one single equation model where its current values are explained by its lagged values, whereas a VAR model is an n variables n equation model, which expresses each variable as a linear function of its own past values, the past values of all other variables being considered, and a serially uncorrelated error term. So popularity of VAR models was impulsed by Christopher Sims due to his research paper from 1980 called Macroeconomics and Reality. The main premise is that VAR models provide a coherent and credible approach to data description, forecasting, structural inference, and policy analysis. The main use of VAR models is for forecasting macroeconomic variables such as GDP and inflation, and for policy analysis. So let's take a look now at a formal representation. This is an example of a bivariate bar because it contemplates two variables such as y and x, and it contains one lag. That's the reason why it has a 1 here in brackets. So as I have explained before, it's an equation. So we have two equations. We have a constant term here. Here we have the lagged values of the variable yt, and then we have the lagged values as well of the variable xt. So yt is going to be explained by a constant, its own past values, the past values of the other variables in the model, and the uncorrelated error term. If we want to take this into a matrix representation, the first vector would contain our equations. Our second vector would contain our constant. The main matrix contains the lagged values of yt, the lagged value of xt, and here the same goes for the variable xt here. It's going to be explained by yt minus 1 and xt minus 1 here. So what are some of the assumptions of the bar models? Well, variables yt and xt are stationary. Logs and differences can be applied if required. Some of these transformations may be required in order to make our variables stationary. UT and VT, which are our error terms, are white noise disturbances, and they are commonly called innovations or shock terms. And finally, the coefficients in the main matrix are estimated by OLS. So now let's take a look at our example, which is a Stockton-Watson 2001 paper called Vector Autoregressions. What we are going to do now is follow an example step by step. We're going to be replicating this research paper and using vector autoregression models. So just as a summary, the authors review how bar models perform the four tasks that econometricians do, which is data description, forecasting, structural inference, and policy analysis. In order to do so, they set up a bar model to see how monetary policy affects inflation and employment, and also review the Phillips curve. The variables that they use in their model is inflation, unemployment, and the Fed fund rate. The frequency is quarterly data and goes from 1960 to 2000 Q4, and this data is available in the description of the video, so feel free to download it and follow the steps one by one. So this is the representation they do. They have inflation, which is going to be explained, as I said, by past realizations of inflation itself, past values of unemployment, and past values of the Fed fund rate. And similarly for unemployment and the Fed rate, it's going to be explained as well, past values of inflation, unemployment, and the Fed fund rate. So now let's set up this model in Eviews. We're here in Eviews. What we are going to do is we're going to select our variables, inflation, unemployment, and the Fed rate. We're going to click the right click. We're going to go with open, and we open as a bar model. So here it tells us what type of bar we want. We are going to just go with the standard bar, but you could technically be working as well with vector error correction, Bayesian bar, switching bar, or mixed frequency, which I may be covering in the future, but for now we're just going to stick with the standard bar. Here goes our endogenous variables as inflation, unemployment, and the Fed rate. And here goes the lags that we are going to be using in our model. Just for now, we're going to stick to 2, which is the default, and then we're going to see how we can select optimally the amount of lags to be included in the model. And here is the exogenous variables. Here we only have a constant. That's what the authors did in their paper. But alternatively, some other authors, what they do is they include dummy variables or other exogenous variables here. But like I said, for now, we won't need this. We're going to hit OK. And here now we get our estimates. We have inflation, unemployment, and the Fed rate. And as you can see, because we have selected two lags, it here shows the two lags for inflation, the two lags for unemployment, the two lags for the Fed rate. Here goes the constant. And here what shows this output is just the normal OLS estimation outputs, which is the R square, log likelihood, the model selection criteria like a Kaike-Schwarz, um, and some other informations that we'll cover later. Lag length criteria, the importance of an appropriate lag length is that if the lag length is too small, the model is going to be misspecified, while if the length is too large, degrees of freedoms are going to be wasted. So there are two options to work around this. You can let the frequency of the data determine the lag length. If you're working with annual data, it's going to be 1 lag. Monthly data will be 12 lags, and quarterly data is going to be 4 lags. Option 2 is using one of the criterions to determine the lag length criteria, which would be, for example, Akaike, Schwarz, and Hannan-Quinn. Just as a note, there should be no autocorrelation at the selected lag. So whether we choose option 1 or 2, we have to verify that there will be no autocorrelation at that specific lag. So now what we are going to do is going back to our Eviews. I'm going to show you how to re-estimate the model. We would select estimate. The authors have used 4 lags. I invite you to download the paper and follow through. They have used 4 lags. There's no autocorrelation at this lag selected by the authors, which I'm going to show you later. But let's go with then OK. And now you see that it's going to re-estimate our model with 4 lags. If you were to use a selection criteria, what you would do is go to View. You're going to go to Lag Structure, and you're going to select here Lag Length Criteria. What you're going to see in these results is that it's going to report us here some criterions. The most commonly used are Akaike, Schwarz, and the Hannan-Quinn. And here it's going to tell us the lags. It goes from 0 to 8. That's what we have specified earlier. But you could select more lags with no trouble. And this star shows that it's significative. So the Schwarz is suggesting to use 2 lags. Hannan-Quinn is suggesting to use 3 lags. And then Akaike is suggesting to use 5 lags. The difference between these criterions is how much they're penalized for using more lags. So that's why the Schwarz criterion uses less lags than the Akaike. And Hannan-Quinn is somewhere in between Akaike and Schwarz. That's the reason why it's suggesting 3 lags. However, like the authors have done in their paper, they have used 4 lags, and I'm going to show you a little bit later the decision for this, which is most probably related to autocorrelation in the residuals. So now let's take a look at the VAR stability conditions and residual diagnostics. The stability of the VAR system implies stationarity, and in the literature, stability condition is also referred to as stationarity conditions. So if all inverse roots of the characteristic R polynomial have modulus less than 1 and lie inside the unit circle, the estimate VAR is stable. If the VAR is not stable, diverse tests conducted on our VAR model may be invalid. Also, impulse response standard errors are not valid. So now let's go back to our reviews. We're going to select here View. We're going to go into Lag Structure, and we're going to select our roots graph. As we can see here, it's showing us the unit circle, and all the roots lay inside the circle. However, if there's some values that you're not sure about it, you can click in View. You can go to Lag Structure and report the table. The table is going to show us the values from the bigger value to the smaller value, and what we can see here is that the biggest value is 0.96, which is smaller than 1. So although it's kind of close, this is still acceptable. But definitely if you have values that lay outside the circle, you should definitely be re-estimating a different model with different amount of lags. Okay, so now that we have determined that our model is stable, it's time to check for our residuals. So let's go back to Eviews now, and I'm going to show you how to do this. We're going to go into View, we're going to go into Residual Tests, and then we're going to hit Correlograms. We're going to let 12 lags as a default. We're going to hit OK. And what you have to check here is going to show us is the autocorrelations within the 2 standard error bounds. So you have to check that these values lay inside the 2 standard error bounds, And we can see that overall, all of these values lay inside the two standard error bounds. So that's a good signal. If you have all these values that are very critical and all laying outside the two standard error bounds, then you will definitely want to re-estimate the model using a different lag selection. The next thing that we're going to do now is go back to view, residual test, and we're going to go into autocorrelation test. We're going to select 4 lags. Hit OK. Here reports our residual zero correlation test. The null hypothesis is that there is no zero correlation at the lag specified. In this case, we have 4 lags. And here reports the p-value. We're going to use as a default the 5% significance level, meaning that if the p-value, in this case, is bigger than 0.05, we do not reject this hypothesis. While if the p-value is smaller than 0.05, we're going to reject this hypothesis and we're going to say that there is correlation. So as you can see in lag 1, there is correlation, so using one lag is not appropriate. Using lag 2, remember that, for example, the Schwartz criterion told you to use 2 lags, would have been okay. There's no autocorrelation here. Using 3 lags, there would have been autocorrelation, and using 4 lags, it's appropriate as well. There's no autocorrelation. So that's one of the reasons why the authors have decided to go with 4. Also, it has to do with being query data. There's no autocorrelation at this lag. It's a decent amount of lags for our system to be able to show some dynamics. So now let's go back to our slides. We have decided that our model is stable and that there is no autocorrelation at the selected lag. So that's a good thing in our model. So now we can take a look at the Granger causality test. So the test of causality examines if lag values of one variable helps to predict other variables in the model. The Granger test null hypothesis is that X does not Granger cause Y, and the alternative hypothesis is that X Granger causes Y. So if we reject the null hypothesis, then what we're going to be saying is that X Granger causes Y. So let's take a look at that in Eviews. In Eviews, we're going to go into View. We're going to go into Lag Structure and select the Granger causality test. It's going to show us the dependent variables, inflation, unemployment, and the Fed rate. And here are the explanatory variables. And it's going to be reporting the corresponding p-values. Remember that the null hypothesis is that this variable does not Granger cause, inflation. So for example, unemployment does not cause inflation. Is this true or not? Well, because the p-value is smaller than 0.05, what we are saying is we reject this null hypothesis. Consequently, unemployment does help to predict inflation. The Fed rate, because the value is bigger than 0.05, then the Fed rate does not help us to predict inflation. Let's go to unemployment, and similarly the same. Here, inflation does not help us to predict unemployment. However, the Fed rate does help us to predict unemployment. And in terms of the Fed rate, what we can see here is both inflation and unemployment help us to predict changes in the Fed rate. Yes, so if in inflation or unemployment changes, the Fed rate will be reacting and be changing the rate. So again, the Granger causality test, what it shows us is whether or not these variables will help us to predict current values of the dependent variable, right? So this is going to be all the content for this video. I don't want to make this video too long, but in the next video, what I'm going to be showing you is impulse response functions and the variance decomposition. So I hope that you found this video useful. I invite you to subscribe to my channel to keep getting content related to economics research and how to use Eviews, Stata, and also how to use LaTeX with Overleaf. It's really important that if you're going to be writing assignments or writing a research paper, you know how to use LaTeX, because that's going to help you to present your work in a more fancy way, in a more formal way, and in a way that it's used normally in the academics. So once again, thank you very much for watching and have a great day.